I'll admit it. When I was an undergraduate, I really struggled with getting past all those numerous facts and details and getting to the point where I really understood how the concepts all related to one another and seeing the underlying pattern, the core concepts that kept repeating themselves throughout my biology courses. In this episode, I'm going to share a learning strategy that has really helped my students get to that point.
Welcome to the A&P Professor. A few minutes to focus on teaching human anatomy and physiology with host Kevin Patton.
In this episode, I discuss news regarding neurogenesis in the adult brain, an analogy about cells and ions, and a learning strategy called running concept lists. Can adult human brains produce new neurons? Well, if you had been a student of mine back in my early days of teaching, my answer to you would have been a definitive no. Adult human brains cannot produce new neurons. And it wasn't just me. Everybody thought that. Actually, this idea goes back more than 100 years to the Spanish researcher Santiago Ramon y Cajal, who's considered to be the father of modern neuroscience. And he stated this, dogma that states that neurons cannot be produced in the adult human brain. That capability stops fairly early in human development. It wasn't until the 1960s when some research started to hint at the fact that, maybe that's not really true. Maybe there are some neurons that continue to be made even in adulthood. But, of course, that was going against the strongly held dogma and widely held dogma of the time. So it really never took hold until, a few decades later in 1998, when a paper came out that pretty clearly seemed to show that in the adult human hippocampus, at least, that new neurons were being produced. So it didn't take long before that spread like wildfire. And now, if you would have asked me a week or two ago, in one of my human anatomy physiology courses, can the adult brain produce new neurons? I would have said, yeah, we didn't used to think so, but now we know that that, in fact, is true, that some new neurons are being made even in adulthood. Okay, the story might be changing again. Just a few days ago in the journal Nature, a new paper came out that provides what I think is some strong evidence that suggests that neurogenesis, that is production of new neurons in human brains, stops early in development. Probably in childhood, it decreases until about age 7 or so, and then that's it. No more neurogenesis through the rest of childhood, adolescence, and adulthood. And this is based on some evidence from brain tissues that were collected from various subjects over the lifespan, that is fetal tissue all the way up through elderly adult tissue. And this scan of the tissues looking for newly produced neurons in the brain didn't find any in the older brain specimens. So this is providing evidence that maybe that dogma is true, at least in essence, is true. So this has already been very controversial. And so what does that mean for our teaching of human anatomy and physiology? Well, I think it means that science continues to work. I mean, this is how science happens, right? This is how discoveries occur. We have hypotheses that are thrown out. We start investigating those hypotheses. We get some early data that seems to maybe support a hypothesis. In this case, it did. And so more and more people are convinced that that's the reality. And then when evidence shows up that sort of breaks down that or challenges that hypothesis, we're resistant to the change. And that makes sense. We don't want to just be changing our minds every week as new information comes out. But over time and with very, very convincing research, then we do sometimes throw out that old idea. So I think this is something we should bring into our A&P class. I think that, the definitive answer is still kind of wobbly out there, especially in light of this new research that just came out. But throw that out there and say, well, look, a lot of neuroscientists believe that neurogenesis does occur in the adult human brain. Recent evidence has come out that challenges that. So what it's going to end up being, we're going to have to see. So what do you think? And that might be a spark of a really good discussion. Or at least we can throw out there the fact that here's a statement that we're making, or here's a concept that we're teaching that isn't set in stone, that answers are still being investigated. I don't think I've ever met an A&P teacher who does not use analogies in teaching their course. And I have one that I think will be very useful to a lot of you, or it might give you an idea for adapting it for your own course and your own teaching persona and approach to helping your students. At the very beginning of the course, when I'm not introducing, but reviewing the idea of ions and how important they're going to be in our discussion of human anatomy and physiology, I give them this principle, and I tell them that if they remember this, it will take them very far in understanding the stories that I will be telling them in A&P about how the human body works. And it's this: cells. Cells, let's pretend they're conscious, and I'm not so sure they're not conscious, but we'll pretend they're conscious, and I will tell them that cells hate certain ions. They hate calcium ions. Cells hate sodium ions. And how do I know this? Because whenever calcium ions leak into a cell, the cell goes through a lot of effort in the form of calcium pumps to pump it out. And the same thing with sodium. There are sodium pumps, actually sodium-potassium pumps, that pump out the sodium out of the cell. Sodium leaks in, gets pumped right back out again. We can think of them as some kind of nasty little beast. A lot of people are afraid of snakes. Now, I have the opposite view of snakes in general, but a lot of people, I'll ask my students, if a snake came into this classroom, what would you do? And of course, then they're all saying, scream, yell, jump up on the desk, so on, shoot it, cut its head off, and so on. And I said, well, what would you want me to do? Get rid of it. I said, okay, so, I'm the calcium pump. I'm the sodium pump. That's something we don't want in here. So when the snake comes in, I will grab it and I will throw it back out in the hall. And if it squeezes back in under the door, guess what I'm going to do? I'm going to grab it and throw it back out in the hall again. And I'll just keep doing that over and over to make sure that snake does not get to you. And so that's what the cell does with calcium and sodium. Just like most of my students hate snakes, cells hate calcium and sodium, and they pump it out. But wait, you might say, what about the large number of calcium ions that are stored inside of the sarcoplasmic reticulum of muscle fibers? Doesn't that break down the analogy? Well, number one, analogies never work 100% because they're analogies. They're imperfect. But this one actually does work. If we imagine these snakes that are coming into the classroom, but we don't want them in the classroom, I, as the calcium pump, can grab a hold of the snakes and throw them back out into the hallway. And as they come back in, I can throw them out again. But I could alternatively put them into a sack and tie the sack shut. And that'll keep the snakes away, hopefully, for a little while. And what happens if they slither out of the sack? Well, I'm just going to pump them right back in. And if they slither out, I can pump them right back in. So later on in the course, when we get to muscle fibers and how they work, we can be reminded of that analogy and say, well, remember that what the calcium pumps are doing? Remember that this muscle fiber hates to have calcium. So if calcium leaks into the muscle fiber, it gets pumped out. But some of it gets pumped into the sarcoplasmic reticulum. And there is a circumstance under which it will leak out and then we'll immediately pump it right back in. So during excitation, it's going to leak out because of the voltage change in the membrane, but right away the calcium pumps are going to pump it right back in, and now we're back at relaxation again. So it still works. And then I ask them, well, what if there's some kittens that wander into our room? Should I throw those out in the hall too? Like, no, keep those in there. I said, what about puppies? And like, no, you don't need to throw them out in the hall. We love puppies. And so I say, are there any ions like a puppy? And usually I have to coax them along a little bit until they go in the right direction. But what about potassium? Whenever potassium is hanging around a cell, what do? We pump it in. It's that same sodium-potassium pump. So I tell them, if I'm playing the role, sometimes I even act this out. If I'm in a room where the door to the hallway is, at the front of the room or in an area that they can all easily see, I'll act it out and pretend to be grabbing a snake and pushing it out. And while I'm facing the hallway, I'll grab a puppy and pull it in. And then grab a snake on the inside and push it out, and then grab a puppy and pull it in. And so I'm pretending to be the sodium-potassium pump. And I then take it a step further, I guess, and tell them that if you just memorize those facts, even though it's kind of crazy, it's kind of silly, it's reinforced by the silliness. Learning research tells us that crazy visual images help us remember things. So they have this crazy visual image of the snakes and the puppies and so on. And that's going to help them as they get further along. And then it's not long before we start talking about membrane potentials. And they just know that, hey, calcium is going to get pushed out. And it even comes up in maybe some unexpected ways later in the course when we're talking about making bone tissue, osteogenesis. And we see that, the cells, the osteoblasts, what are they doing with calcium? Pushing it out. They're getting calcium from the blood and they're pushing it right out. And it's all accumulating on the outside of the cells. The calcium of bone tissue is not in the bone cells. There's very little in the bone cells. If you want to find calcium, you look outside of cells. If you want to find sodium, look outside of cells. There's a lot of sodium outside of cells. Very little sodium inside a cell. Looking for potassium, where do you look? You look inside the cell because cells love potassium like people love puppies. I realize that many of the teaching tips and resources and study strategies that I pass along in this podcast are things that you're already using. Oh, of course that's true. My purpose in doing that is to get you thinking about them again, to reanalyze what you're doing and how you're doing it. And maybe the way I'm doing it will stimulate a thought in your head about maybe trying something different in your class. Or maybe your reaction is, well, I do something similar to that, but I do it this way, and I find that works really well for me. If you find yourself having a thought like this, why don't you say it out loud? But before you do, why don't you call 1-833-546-6336. That's 1-833-LIONDEN, LIONDEN. Or you can email podcast, PODCAST, at theapprofessor.org and let us know about that. I would love to be able to share especially a little voice clip or voicemail that you've left on our podcast line. And or if you'd like to be interviewed, call that number too and leave your contact information and we'll do it that way. But I'd sure like to get this to be more of a community effort and less of Kevin talking about what he does all the time. And so please do call or write in with your contributions or your suggestions for resources that you found to be useful in your teaching of human anatomy and physiology. I'd like to spend a few minutes talking about a learning strategy that my students have found to be very helpful in their study of human anatomy and physiology. It's called a running concept list. And it's the kind of learning strategy that takes students beyond the learning of the basic facts into that area that we really want them to get to, but often have a hard time getting them there, and that is the area of learning where they're drawing connections between concepts, where they're looking for and actually seeing the underlying principles of human structure and function, those underlying patterns that help them not only understand the material and the ideas that they need to be learning right then and there in the course, but also preparing them for the kind of learning that they're going to need to be doing as time goes by, later in our course, in subsequent courses, and finally in various clinical applications throughout their career. So how does a running concept list work? That's the best place to start, I would think. It's a list. That's all it is. I mean, it's very simple. And the simpler a learning strategy is, the more likely it is we're going to be able to get our students to do it, right? And I've had probably hundreds of my students using concept lists. And what I tell them to do is get a loose leaf binder and with some blank pages in it. And that's going to be their binder for concept lists. Now, they can also just use, the back section of whatever notebook they're already using and so on. But I think starting with a brand new binder is a good idea because this is going to be a tool that is going to be changing over time. They're going to be engaging with this and altering it over time, maybe over their entire career. And the loose leaf binder just lends itself to that. So what I tell them to do is every time a concept comes up, more than one time, then that gets a new page in their binder of concept lists. That is, you start a new concept list. So what do I mean by a concept? Well, it could be a variety of things. It could be something like negative feedback or positive feedback or membrane receptors or membrane transporters or maybe signal transduction. One that I use often as an example because it starts early in the course, and that is calcium. Calcium is an actor that shows up in the story of human anatomy and physiology time and time again at a variety of levels. So not only is it important early in the course when we're doing a brief review of the chemistry that we're going to need, and identifying what ions are and identifying a handful of the really important ions that are going to be major players in the story of human structure and function. But it shows up in how many different areas? I mean, look at how many physiological mechanisms involve calcium. All those signal transduction mechanisms, for example, that involve calcium. And it's not just physiological processes that involve calcium, but what about anatomy? Think about bone tissue. And how calcification of the bone tissue gives bone tissue structural characteristics that are very different from other kinds of connective tissues. So if you have a page in your concept list binder that is labeled calcium, well, that's something that comes up more than once, so that makes it a candidate for a concept list. Then every time you run into it, you write down whatever new information you're learning about calcium. And not just new facts about calcium. Oftentimes, when you encounter calcium again and again and again, it's a new application of something you already know. So we're just applying that principle over and over, but in different areas of the body, maybe in different levels of organization in the body. But not only that, but start to also look for insights. That is, look for connections. The more students do this, the more they tend their list and they start adding, oh, here's calcium again. Oh, here's calcium again. What else do I know about calcium? And they start to assemble more and more knowledge, and they have page after page maybe of all these things they're learning about calcium, which in itself is a good process, right, of reviewing and consolidating information. Not only is that helping them draw connections between all what our students often consider to be separate topics. I mean, that was chapter 1. This is chapter 2. That's separate. Well, it not only blurs that line, which we want to blur, but it also trains them to start looking for those insights. They start seeing as they write down this stuff like, oh my gosh, here's something that I should have understood when I first ran into calcium being used as in signal transduction. I should have recognized or realized how signal transduction works, but now it's becoming clear. Now that I see calcium being involved in this kind of signal transduction and that kind of signal transduction, or in this process or that process, I'm starting to have insights about how all these different processes work. Not just the calcium's role in it, but how the processes themselves work. And the more of those insights that they can see, the more that they're going to get in the habit of looking for those insights. So as they go through the course, they're running their list, right? What that means is they're reviewing it occasionally because they want to look through and say, okay, I have a calcium page. Have I learned anything new about calcium? Oh, yeah, there was that one part, so let me put that down. And then they flip over and they see a page on sodium and think, oh, yeah, I learned some more stuff about sodium too, its role in the body. And then the next one is signal transduction. Oh, yeah, well, we were talking about calcium's role in signal transduction, so let me put that on my signal transduction page as well. So the students will be repeating some of the information they're learning on multiple pages within their concept list binder. And again, that's good, right? Because the more they work with that information, the more they process that information, the easier it's going to be to retrieve it later, and especially retrieve it in the process of applying it to maybe case studies or to new concepts that they're going to run across later in the course or in later courses. So running the list means that they're constantly tending to it. And what I tell my students is that we need to really build up a thick binder. And in an ideal world, you're going to have so much information, you're going to need to have multiple binders. And you're going to be making your own encyclopedia of human structure and function. And hey, why not get it beyond human structure and function? Let's start incorporating things we're learning in chemistry class, incorporating things we're learning in microbiology, things we're learning in our nursing class or medical classes or physical therapy classes or neuroscience or pathophysiology or whatever it is that we're doing. If it has anything related, anything to do or in any way related to the human sciences, then go ahead and incorporate that into your master book of concept lists. And so you're going to not only have this growing encyclopedia of information that you have learned, but by tending it, getting in the habit of tending to it, then you're going to continue to build it, and you're going to continue to make cross connections, and you're going to continue to have insights, and that's going to train your brain in how to just do that automatically. Not that I would ever recommend somebody giving up keeping and tending concept lists. It's that we start to do it automatically. We start to want to put it in our list. And I can attest to this because I use concept lists for a variety of things. As a matter of fact, if I look over my shoulder where I'm standing right now, I have a set of notebooks on a variety of different things that I need to keep up on. For example, I have a notebook on learning management systems. And I'll write down in there new skills I've learned. I write down in there steps I need to remember for next semester when I'm, importing information from a prior course. What do I need to remember to do to make sure everything is up to date? I have my little checklists in there and so on. If I go to a workshop on learning management systems, I'll add the new information or new little tricks or shortcuts that I've learned, put it in there. I have another notebook on podcasting. So that I know what settings I need to use in my equipment and then the software I use to produce the podcast and so on. Those are the notebooks I have over my shoulder, but I have another set of books where I keep running. Actually, I have them all in a file drawer. There's so many of them. The various concepts that I build up in terms of human anatomy and physiology. As I've said, I've used this for decades with not only myself, but with my students and the students that do it. And students don't always do what we recommend they do as a learning strategy, right? But those that do and really stick with it really have benefited from it. I've gotten really good feedback on this, and I've even gotten feedback from students that I see years after I've had them in class, and they tell me that they're continuing that process in nursing school and beyond. And so it's something that I think is not only useful for our immediate goal of success of our students in our human anatomy and physiology courses, but I think it's also useful in the broader goal of providing students that not only the core concepts, but the tools they need to continue to apply those core concepts and continue to gain insights about the core concepts and the patterns of those core concepts as they move way beyond our course. So if you go to the show notes for this episode, or you go to the approfessor.org and find the episode page for this podcast episode, you're going to see a bunch of links. And included in there is a link to a page that I provide my students that very briefly runs down how to do a running concept list. And embedded in there is a video that kind of walks them through the process of a concept list. And you're welcome to link your students directly to that, maybe in your syllabus or your learning management system, course webpage, whatever. Or you can use that as a template to build your own set of information in your own course about running concept lists.
The A&P Professor is hosted by Kevin Patton, professor, blogger, and textbook author in human anatomy and physiology.
This podcast was produced without the use of hormones. Wait, that can't be true. I've got a lot of hormones doing their jobs at this very moment. Never mind.